third and last lecture, and it will be about Feynman diagrams. I will try to give you a very uh, uh, short but self-contained introduction to Feynman diagrams. So even if you never used them before, hopefully everything will make sense. And then in the end, I will try to explain you why we believe now that Feynman diagrams for the unitary Fermi gas, or more generally for strongly correlated fermions in continuous space, actually make sense and can be used to do high precision calculations. So, this is my chapter 6, Feynman diagrams, and to start with, to begin with, I will do it for the lattice model for pedagogical purpose. So I remind you of the Hamiltonian of our lattice model, sum over k in the Franz-Brouillon zone and spin up and down of epsilon k. So epsilon k is the dispersion relation. So for example, it can be h bar squared k squared over 2m, but actually at some point I will talk a bit about the Hubbard model, and in that case, as you know, the dispersion relation will be different. So C dagger k sigma ck sigma plus the on-site interaction with the strength G0, sum over all lattice sides, B3, psi dagger up, psi dagger down, psi down, psi up. It's density, density on site R. So what we want is we want to compute some intensive quantity Q. So for example, it can be the density, let's say the density of spin up, to be concrete. And we want to compute this as a function, of course, of temperature and the chemical potentials, mu up and mu down. And also for a given interaction strength. So, and as you will see, actually, we will compute this directly in the thermodynamic limit. So, meaning that we will directly compute this limit when the volume goes to infinity of, so in the case of the density, it's of course psi dagger up, psi up at point, it doesn't matter, let's say at point 0. So this corresponds to the equation of state, of course, density as a function of temperature and chemical potential. So the idea is very simple. Here we can just expand in powers of the interaction, in powers of G0. And it turns out that the coefficients of this expansion can be represented by Feynman diagrams. It's just a convenient trick to represent this expansion. So to show you how it works, let me just start by drawing the Feynman diagrams for this quantity, for the density. So the lowest order Feynman diagram looks like this. So you see that you have a spin up line that is called a propagator, which starts at 0, because we have here a psi dagger at 0, and then we have to annihilate again at 0. So the simplest thing we can do is just to draw this diagram. Then, slightly more complicated, we can draw this diagram where, so we create again our spin-up particle at 0, and then here we put an interaction vertex. So it's a 4-point vertex. And the diagram looks like this. So you will see that the general rule is that we should use interaction vertices where we have two particles of opposite spin which arrive and two particles of opposite spin which go out, and this just comes from these operators here. So let's continue a little bit the exercise. So let's draw the next diagrams. So there is, I need a bit of space. So there is this one, which looks like a Mickey Mouse. So our particle is created here, then it interacts with a spin down, and then with another spin down. We can also draw this one. And okay, I will stop putting all the arrows and the spins, but you can put them if you want. And then finally we have this one. For this one, actually, I will put it. And then, of course, we have we can continue the game infinitely. So you see that actually this one, well, you will see in a minute, but for now, believe me that this one is just the density, so the equation of state for the ideal Fermi gas. And so it's actually independent of the interaction. It's of order G0 to the power 0. This one is of order G0 to the power 1. So it corresponds to the mean field correction. And these ones are of order G0 squared. So the general rule is that for each vertex, you have one factor G0. So so let me explain a bit more now about these rules, which are called the Fineman rules, which tell you how to convert a given diagram into a formula that will give you a contribution to what the quantity you want to compute. So in our case, to the density. And also we should have the rules about which diagrams to draw. So the diagrams to draw are just all the connected diagrams. Sorry, connected. And the diagrams are constructed, as you can already understand from the example, using the following building blocks. So we have this special point. That's because we are calculating the density. And then we have interaction vertices that I already mentioned with opposite spins. And that's all. We just need to connect these things with lines. Now, how do we calculate the contribution for a given diagram? because of course, so for each diagram we want to calculate a number, which will be the contribution to the density. So for this, I need to define a function g0 sigma of r and tau, which is called the propagator, and it's defined as follows. It's minus expectation value of psi sigma of r tau, psi dagger sigma of 0, 0 if tau is positive, and if tau is negative, what you should do is to swap these operators and also change the sign, because we have fermions. So that's called a T product. And then it's pretty simple. So let me explain how it works for one example. Namely, I will use this last diagram over there as my example. So I will draw it again here. So first of all, what you should do is that for each interaction vertex, you should introduce a position and a time. So for this vertex, let's say that this is vertex 1, so it will be r1 tau 1. And for this vertex, let's say it's vertex 2, so it will be r2 tau 2. And then for each line, you will have a factor g0. So for example, for this line here, you see that this line goes from here. So here actually it's 0, it's position 0 and also time 0. So so this line, you see it goes from 0, 0 to r1 tau 1. So for this line, and leave some space in the front here, so this line is g0 and it's a spin up. So it's g0 up of r1 tau 1. And this makes sense because you see that this corresponds to creating a particle at 0, 0 and destroying it at r tau. So here it's destroying at r1 tau 1, just like in this diagram. And then so you should do the same game for all the other lines. So for example, this line, you see that it's g0 down, and it goes from r1 tau 1 to r2 tau 2. So therefore it will be r2 minus r1, tau 2 minus tau 1, because actually we have translational invariance. And okay, I think you got it. So you have 3 other lines here, and each of them will give a factor g0 of something. Then what you need to do is these variables r1 tau 1, r2 tau 2, you should integrate on these variables. So sum over r1 b cubed integral from 0 to beta d tau 1, and beta here means 1 over kbt, sum over r2 b cubed integral from 0 to beta d tau 2. And tau, by the way, it's called imaginary time. By the way, I forgot to mention that Here, what do I mean by these things? So the definition here, this is the Heisenberg picture. So when you have some operator of R tau, this is by definition, it's A of R, and you put sandwiched in between the evolution operators e to the minus tau h, e to the plus tau h. So that's why it's called imaginary time, because instead of putting it here, you put tau. But tau is real. And actually, it's convenient instead of h to put h prime here, where h prime is h minus the sum over sigma of mu sigma and sigma. So it's a grand canonical Hamiltonian. So we are almost done with the Feynman rules. Just two more things. So this thing, it should be, as I already mentioned, there should be a factor g0, and in fact it's minus g0 to the power 2 in this case, because we have two vertices. And the last point is that there is also a sign that you have to put in the front, and I'm a little bit out of space. It's minus 1 to the power NL, where NL is the number of loops. Actually, internal loops. So, for example, in this diagram, you see that there is one loop, which is this one. So, a loop should be the same spin. So you see that you can, just with the spin down, you can make this loop. And that's the only one. So in our case, this is equal to 1. And this thing is here because of fermionic antisymmetry. So that's the Feynman rules, and just believe me that this is correct. I mean, it's quite standard, and it's a bit cumbersome to derive, but it's correct and it's very convenient. Any questions? Yeah. No, because it's only the internal loops. See, internal, so meaning that you are not allowed to go through this external point. Okay, so yes. Let's say that you should follow the arrows. Just follow the arrows, like in the traffic. It's the same diagram. So, I mean, if you take this diagram and you flip it around, then everything will be going in the other direction, but it's the same diagram. We consider that this is the same diagram. You cannot switch the things independently from each other, because you should always respect this rule. Sorry, let's discuss it later. I mean, it's not very important. Yeah. Okay. So, so in this way, you see that we have formally a series for our density, which looks like sum from n equals 0 to infinity of an, where an here is the sum of all the contributions of all diagrams of order n, meaning with n vertices. So they are of proportional to g0 to the power n. So in other words, we just made a Taylor expansion in powers of g0. And this is what we will call the bare diagrammatic scheme. It's the simplest thing you can do. So note that, as I already mentioned, this actually works in the infinite volume. You can immediately work with the infinite volume in the thermodynamic limit. And the reason for that is that all the diagrams are connected. If you had disconnected diagrams, then in the infinite volume limit, the sum over all the positions would diverge. But here, because the diagrams are connected, the sum remains finite. Okay. And by the way, this is different from so-called determinant diagrammatic Monte Carlo of Burowski and Gulko, where they actually have disconnected diagrams, so they have to work with the finite volume. Yeah? It's called imaginary time, but I mean, that's just a name. I explained why this name is natural, but I mean, there is nothing to understand here. I give you the rules, and you should believe me. Okay? So note that this formalism can only work in the normal phase. Because if you are, if you were in the superfluid phase, then as you have or will learn from Mira, so you will have expectation values of psi up, psi down, which are non-zero. And you can see this in BCS theory, as Mira explains in her lecture. And therefore, we would need to introduce some propagators which look like this, where you destroy a particle here and you destroy here as well. These are called anomalous propagators. So today I will not consider this, and I will restrict to a normal phase. So now you might think, okay, if I want to do the resonant Fermi gas in continuous space, I want to take the limit, the continuum limit, lattice spacing goes to 0. However, then it turns out that you have a problem, because in this limit, the contribution of each diagram goes to 0. So you cannot take this limit just blindly. So if you want to do calculations in using these diagrams, you need to keep a finite lattice spacing B. And then, of course, you need to make your B smaller and smaller and then extrapolate. But actually, this would be quite painful, because so each diagram becomes very small, and accordingly, you need to go to very high order if B is very small. So you will have more and more diagrams that will contribute when B becomes smaller. So we don't want to do that. So instead we will use a different diagrammatic scheme that I will introduce slightly later. But before that, I want to make a little excursion. So chapter 7 will be about sign problem and sign blessing. So in this chapter, I will consider, just for simplicity and for concreteness, I will consider the Hubbard model, only in this chapter. Meaning that I will take the dispersion relation, which, as you know, Joseph mentioned it. It's -2 times hopping, sum over all directions of cosine ki, the coordinate ki of the momentum. And okay, in the Hubbard model, we can just take the lattice spacing equal to 1. There is no reason to keep lattice spacing which has some value different from 1. And then G0 is usually denoted by U. So, what is the fermionic sign problem? It's basically the following. So, if you do some Monte Carlo simulation, in your Monte Carlo simulation, whatever Monte Carlo method you use, you will typically have to compute some average, which looks like this: 1 over capital I, sum from little I equal 1 to capital I of Ci, where Ci is a random number. And as usual in Monte Carlo, this average, if you have a sufficiently large number of samples, a sufficiently long simulation time, this should converge to some average value, which is equal to the physical result that you want to compute. So, for example, the density. Now, the problem is that for fermions, these random numbers can be positive or negative, and if you take the sum of all the positive ones, it will be nearly equal to the absolute value of the sum of the negative ones. So, meaning that you see that your signal to noise ratio will be very bad, because you are trying to compute something which is very small compared to, so the thing you are trying to compute, sum over Ci, in absolute value, it will be very small compared to the sum of the absolute values. So that's pretty bad, and in practice it implies that you will need a long CPU time, you will need a large capital I in order to have accurate results, in order to have your statistical error small compared to your signal. Okay? So I will now consider two concrete type of Monte Carlo methods, and I will mention why. Yes. Basically, it comes from the fermionic sign problem. So it comes from the fermionic sign, which comes from the fermionic antisymmetry. So one type of method is the methods which work in finite volume. So that's the, I would say, conventional quantum Monte Carlo methods, where you simulate a finite size system with a certain volume V. And then at the end of the day, you will plot your results as a function of V, and you will try to extrapolate to the thermodynamic limit. So maybe the most widely used such methods, it's so-called auxiliary field quantum Monte Carlo. The name doesn't really matter here. So the point is that because of the fermionic sign problem, what happens is that the statistical error will grow as a function of volume. When you increase the volume, it will grow exponentially with the volume. There is an exception, which is if you are at half filling, then there is no sign problem. But let's forget about this particular case. So in practice, this very quick increase as a function of volume is really prohibitive. So basically, it prevents you to reach the thermodynamic limit. So what people usually do is when they use this method, nowadays, they make an approximation, which they call constraint path, which is based on some trial wave function. And this allows them to get rid of the sign. So there is no more sign problem, but the approximation is not controlled. So if the trial wave function is good, the result will be quite accurate, but anyway, it will never be exact. Nevertheless, also recently, they claimed that they are confident that there are stripes in the Hubbard model. So I put the reference in the notes if you want to take a look. But to make this claim, they had, of course, to compare lots of different trial wave functions, and actually they also compared with other methods. So another extremely popular and successful class of methods is dynamical mean field theory and its cluster extension, where you replace your infinite lattice by a single site or a cluster of sites. And here, again, you have a sign problem because your statistical error will increase exponentially with the volume of your cluster. And in order to get exact results, you need to extrapolate this to infinity, and this is very challenging. So it can be done only in certain situations. In general, today it cannot be done. So a completely different class of methods is to use what I will call an infinite volume approach, which is a method which works directly for the infinite volume. And as I already explained, the tool to do that is to use connected Feynman diagrams. So in general, this research program is called the diagrammatic Monte Carlo, and the idea is quite simple. Let's try to calculate connected Feynman diagrams up to as high order as we can, and let's see what we can get from that. So you are trying to calculate some quantity Q, intensive quantity Q, and you will write it as a sum diagrammatic series. AN is the sum of all order n diagrams, and of course in practice you can only go to a certain order n max. So typically it's 8, 9, it depends on the problems. So here the idea is to use again a Monte Carlo algorithm in order to calculate the sum of the diagrams. So I will have no time at all to talk about these algorithms, but let me only say that here we also have a sign problem. And this basically comes from the fact that we have this -1 to the power number of loops for fermions. And as a result, different diagrams nearly cancel each other. So, so as a result, our CPU time as a function of order grows quickly. In the best case, it grows exponentially. In the best case being a recent algorithm invented by Riccardo Rossi, and I put the reference also in the notes. However, we also have the sign blessing. In the following sense. As I already mentioned, there is a massive cancellation between different diagrams. And this implies that the sum of all diagrams will be much smaller than the number of diagrams, which is of the order of n factorial. And in fact, this series, this sum of an, can even converge. In which case, of course, an will actually decrease exponentially with the order. And it turns out that this happens for the Hubbard model if the interaction is not too strong. So in practice, people have gone using this bare diagrammatic scheme. People have gone up to u over t equal to 4. Well, in fact, they used a slightly more advanced scheme than the bare one, but it's almost the same. And this already allowed to get state-of-the-art results, so which could not be obtained by any other method. So if I summarize the situation, so on the one hand, it's exponentially expensive to go to high orders. It's really expensive to calculate high orders, but on the other hand, it pays off very well, because if you truncate at order n, then the error that you make is actually decreasing exponentially with n. So it's quite easy to show, even though we realized that only recently, it's easy to show that the net result of these two things, basically the sign problem on the one hand and the sign blessing of the other hand, is that the CPU time will only increase as a power law as a function of the total error. So the total error coming from the statistical error and the truncation error. And such a power law scaling is actually the best possible scaling that you can hope for any Monte Carlo algorithm. And by the way, there is, contrarily to a common belief, there is absolutely no fundamental limitation that would prevent this coming from NP hardness or whatever. Okay, so now let me move to the next chapter, unless there are some questions. Yes? Yes, that's the typical situation if you have a, because remember it's a Taylor series, and you know if it converges, you are inside the convergence radius, and therefore it converges exponentially. Yes. Yes. And also the in the definition of the propagator, when you change, when the time is negative, there is no minus sign. Okay, so next chapter is finally the Fineman diagrams as promised for the resonant Fermi gas. So in practice, we only did the unitary Fermi gas so far, but in general, the method is applicable for any scattering length. So that's why I put resonant Fermi gas. I will abbreviate it by RFG in the following. So here, the idea is we want to really directly simulate the zero range model. So we don't want to have a lattice, and then extrapolate to the continuum limit, but we directly want to work in continuous space with zero range interactions to directly tackle the actual problem. So what we have already seen in the chapter 6 is that we can write down, at least formally, we can write down this bare series. So let me draw it again. And as I said, you cannot just take the continuum limit on these things because each diagram will go to 0. So instead, what we will do, and I mean that's quite a natural thing and a standard thing in the literature, is to define an object which is sometimes called a T-matrix, but now it's a T-matrix in the medium, as opposed to the T-matrix in the vacuum that Mira discussed for the two-body problem. So the object is represented by such a line, and it's defined in terms of diagrams like just the vertex plus the two vertices connected in this way, plus 3 vertices connected in this way, etc. So sometimes people get confused if you draw it like this, and they prefer to add so-called external lines. So if you want, I can add them, meaning that this object is supposed to be attached to 2 incoming lines with spin up and spin down, and 2 outgoing lines with spin up and spin down. So this is the definition written in terms of diagrams. I can also write it in terms of equations. Minus gamma 0 of r and tau is by definition minus G0. It's this bare vertex. And turns out here you will need to put delta R0 over B cubed, delta of tau. And then, I mean, this is just because, you know, here this incoming line has to end at the same space-time point. Then this outgoing line will start. So that's where you have to put this delta here. And this guy will be minus G0 squared. And then you see you have G0 up, G0 down of r and tau. So the idea is that this gamma 0 is like a propagator going from 0, 0 to r tau. So here you have to go from 0, 0 to r tau. That's why you have to put this, etc. So having defined this object, now let's go back to the density. So what happens if I draw the following diagram? So you see this diagram looks like this one, but I replaced the bare vertex here by this dressed vertex gamma 0. So this is nothing else. If I substitute this thing in here, I get that this diagram is equal to the sum of the following diagrams. This one. So this is if I substitute this in here. Then if I substitute this thing in here, I get this diagram, etc. So you see that it's quite nice, because now with the single diagram we actually have a sum, an infinite sum of the Bayer diagrams. And now the natural thing to do is, in order to calculate our density, is okay, there is this order 0 ideal gas, which is always there. And then for the order 1, we will take this guy. And then for the order 2, so let me consider first this one. You substitute again the bare vertices with addressed ones, and you will get this guy. For this one, you will get this guy. Then if you substitute here, you get this guy. But actually here you need to be a bit careful, because you see that actually this guy is already, it's this guy which is already contained in this one. Okay, so because we already wrote down this one, actually we already generated this one, and in fact we generated all the ones corresponding to this. So in fact this one we have to remove it to avoid the double counting. So that means that there is some additional Fineman rule. If you work with this dressed vertex, you should not allow these kind of structures to avoid double counting. Okay, this is just a little subtlety. It's not important for what follows. So now we rewrote our diagrammatic series in a different way. And the nice thing is that now we can indeed take the limit b going to 0. So now we can take the continuum limit, and gamma 0 is well defined in this limit. It has a finite limit when b goes to 0. So we can say that we managed to write a diagrammatic series directly for the zero range model. And this is what I will call the ladder scheme, because so instead of using the bare vertex like we had here in the bare scheme, now we use this dressed vertex, which is a sum of ladder diagrams. Actually, these ones are called ladder diagrams. Yes, so I will come back to this story of order indeed. So there is a subtlety about that. So indeed, here it looks like we took these diagrams and we reordered them to get this one. And of course you can worry whether this is correct. A priori it's not justified, because if you take the sum of the absolute values of the diagrams, this will diverge. But as we will see, actually this can be justified. So now we wrote our density as a sum over order of an, and so these new ans, they are different from the old ones. So maybe I should call them AN ladder. So these are the sum of all order n diagrams in the ladder scheme. So meaning that now order n means that you have n vertices, but now the vertices are the gamma 0 lines. Okay, yeah. Yeah, it's just, I mean, that's a technical difficulty. You can kind of forget it. I just mentioned it for completeness. So, yeah. What people do most of the time is they say, okay, let's keep these two diagrams because we can compute them without too much effort, and let's just forget about all the other ones. And this is called Nozière-Schmidt-Rink theory. And it works reasonably well. For the equation of state, it works reasonably well. For the critical temperature, is quite far off. And for the contact, is also quite far off, as I will mention in the end. So of course we want to try to do better than that, but now we have a problem, because actually the series diverges. Actually these ANs, they increase as a function of n. So let me make a quick excursion, a little remark about QED. So in QED, you can also write down Feynman diagrams, you know, with electrons, positrons, and photons. You get, in the end, you get a diagrammatic series which looks like this. So you have all the order n diagrams, and they are multiplied by the fine structure constant to the power n. And it turns out that this series diverges for any alpha. So this was already argued by Dyson using a very nice physical argument, saying that if you change the sign of alpha, the vacuum should become unstable. And it was confirmed by Itzikson, Zuber, Parisi, and Balian, and also Bogomolny-Fatayev, who obtained, or maybe we sometimes they say they conjectured, because it's somewhat shaky derivation, but they found that AN grows like n over 2 factorial. However, as you know, in practice this doesn't matter at all. It's almost an academic problem, because alpha is much smaller than 1, and therefore in practice, if you do order 1, 2, 3, 4, 5 up to 8, which is what people typically can do, actually this thing will just decrease as a function of the order, simply because of each time you multiply by alpha. So even though AN maybe grows, actually because alpha is small, this thing will decrease. Okay, so it will only start blowing up if you reach a very high order. So you can do the exercise based on this thing. You can see that actually it will only blow up at order something like 2e times 137 squared. So we are quite far from being there, and therefore for all practical purpose, this behaves like a series which converges rapidly. And as you know, this leads to results which have been tested with very high accuracy, like digits, 10 digits of accuracy or so. Okay, so that was my little remark about QED. Now let's go back to the resonant Fermi gas. So here we are dealing with a strongly correlated system which has no small parameter. And accordingly, we don't have such a situation. Instead, we just have these coefficients which increase as a function of order. And therefore, if we just truncate the series at some order n max, actually this will just very strongly depend on n max. So if you do that, you will get very depressed because you will have, okay, this is my Nausea-Schmidt ring, maybe it's reasonable, but then it will go like 2 times higher, whatever, it will do some total crap. Okay. So therefore you can wonder, is it useful at all to calculate these high orders? Do they mean anything mathematically? And if so, is it useful? And can we use them to get accurate results? So let me write these 2 important questions. Does this diagrammatic series sum of an mean anything mathematically? Because so far it's just a sort of combinatoric construction. Like we play around with these diagrams, but it's not at all clear whether it has any mathematical meaning. And if so, is it useful? Is it usable to compute, for example, the equation of state with high accuracy and in a reliable way? And now, since quite recently, we think that we can give the answer yes to both questions. So how? Let me explain how we reach this conclusion. Any questions? So we will follow the following strategy. So in order to answer the first question, so to give a mathematical meaning to the sum, we will do the following. We will define or construct, if you prefer, a function q of z, where z is a formal parameter. It's a formal complex parameter, which such that first the Taylor series of our function q of z for z going to 0 plus is given by our diagrammatic series sum of an multiplied by z to the power n. So that in this way we manage to give a meaning to this series. So this series is divergent. A priori it does not have a meaning. What we are saying is that actually these ans are the coefficients of the Taylor series of a certain function. By the way, so I remind you what it means to say that this is the Taylor series. It just means that an is equal to 1 over n factorial, the limit when z goes to 0 plus, so meaning this limit should be taken on the real positive axis approaching 0 of the nth order derivative of q of z with respect to z. Second point, we want that this function, when we evaluate it at z equal 1, this should be equal to the density, the thing that we want to compute. So it should be equal to the exact physical density of our model, of the resonant Fermi gas with zero-range interactions. And finally, Q of z should be an analytic function in a domain that contains the segment 0, 1. So you see, the idea is that when we take z equal 1, if we take this series and set z equal to 1, formally we recover our original series, and so it's quite natural to require that we indeed get the thing we are trying to compute when we do that. And this story about the analyticity is just because we want to connect what happens near z equals 0, where we say we have this Taylor series, with what happens at z equal 1, which is the physical point. And in order to connect these, we should do some analytic continuation, so our function should be analytic. So that's how we answer the strategy, how we answer the point 1. Questions? Yes, it matters, and you will see it if you wait a little bit. Okay, so in order to answer the second point, namely, now that we gave a meaning to this sum, can we use it in practice to compute the equation of state in a way which is accurate and reliable? So for this, the strategy is to design a so-called resummation method R such that, so R will be a function of our coefficients A0, A1 up to A and max. And what we want is very natural. We want, in the limit where n max goes to infinity, so when we take higher and higher order diagrams into account, we want to get Q of 1, which is equal to the density. So basically this resummation method is like a black box. You give it as an input the coefficients of the series, of the diagrammatic series, the sum of all diagrams of order 0, 1, 2, etc. up to, in practice, 9 for us. And it should give you as an output the thing you want. And finally, so not only we want to design this method, and we want to show mathematically that this is true, but of course we want to also check in practice and get the results in practice. So we compute this thing numerically. And as I mentioned, using a diagrammatic Monte Carlo, we can go in practice up to order 9 for this problem. And of course, we will plot, you know, our result R of A0 up to n max. We'll plot as a function of n max. And we will check that indeed this thing, well, in the beginning maybe it does a bit weird stuff, but it indeed looks convergent. And this will be our result. For the error bar, we usually take the last 3 orders to say, okay, this is our error bar. And then we compare with experimental results. And typically we get something like this. So for the density, the most accurate measurement is the MIT equation of state. And typically we get a very good agreement. So now let me explain how do we do this in a little bit more details. So I gave you the strategy. So now let me give you a bit how it works in practice. I mean, how we manage to indeed to do this point 1 and point 2. So for the point 1, the idea is the following. First of all, as I already mentioned, you can interpret this gamma 0 line as the propagator for some boson. So this boson, you can think that it's a pair of spin up and spin down fermions. But here we will really consider it as a different kind of particle, some boson. And so accordingly, in the diagrams, when we have something like that, we will interpret it by saying that this boson turns into a spin up and a spin down fermion. So this boson is converted into 2 fermions. Or other way around, if we have these 2 fermions arriving here, they are converted into a boson. And now we want to achieve this story of the Taylor series. So it's quite simple, because you see that all we want is to formally, we want to multiply the order n diagrams. So the diagrams which have n gamma 0 lines, we want to multiply them with z to the power n. So in order to do that, all we need to say is that we will introduce a sort of coupling constant, square root of z for this vertex, and another square root of z for this vertex. So for each of these vertices where we have one boson which turns into 2 fermions, or other way around, we just introduce a coupling constant, square root of z. And in this way, we get what we want. We get z for each gamma 0 line. So that's the idea. And in practice, it's possible to do this using a functional integral formalism, but I don't have time to write it down or to explain it. But believe me that it's possible using standard tools to define a model where you have fermions and bosons, and let me call it M, which depends on the coupling constant Z, and which has the properties that we want. So it's such that the model, if we set the coupling constant equal to 1, then the model is equivalent to the resonant Fermi gas with 0 range interactions. And in practice, to do this, you just have to integrate out the boson field. And the second point is the story of the Taylor series. Namely, the bare scheme for our model, M of z. So in other words, if we just do a Taylor expansion in powers of z, which is like a coupling constant for our model, then we get some diagrams, and these are exactly the diagrams of the ladder scheme for the resonant Fermi gas. So that's how we, in practice, how we achieve this this goal. Now, how do we achieve the second goal? So for the second point, here it's much more tricky. So in fact, here we are asking the following very general question. We have the Taylor coefficients an of some function, and is this enough in order to recover the function itself? Actually, we only need it at z equal 1. So here there are two questions. First of all, is this unique? So given the Taylor coefficients, is this function unique? And secondly, if so, how do we compute this function in practice? So basically, how do we design this resummation method? So in order to understand this story, let me first do a little excursion. Let's consider the situation where Q of z is analytic at the origin. And therefore it's analytic in a disk around the origin. So let me consider first a very simple example. And now this will be really high school math, but it's already very useful to understand the story. So let me consider Q of z, which is just 1 over 1 plus 2z. Then formally you can expand this in powers of z. And this series is convergent if a modulus of z is smaller than 1/2. And if that's the case, then it converges to the correct result. So what happens in the complex plane as a function of z is that we have a pole here at z equal to -1/2. Okay, the function that has a pole. And we would like to calculate Q of z equal to 1. And for z equal 1, this series diverges. We are outside of this convergence disk. However, it's quite clear what we need to do. We just need to do analytic continuation of the function, of this function, outside of the disk. And you see there is absolutely no problem to do that because the singularity is on the left side. So we can very easily do this analytic continuation. And in practice, and it's unique, of course. There is a basic property of analytic function which tell you that if you have two analytic functions which coincide in a domain, in this disk, in our case, then they have to be identical everywhere. So even here. So it's unique, and it can be computed in practice. And in practice, it can be computed as follows. So let's leave some space here. It's sum from n equals 0 to infinity of -2 to the power n. So this is our sum if we just blindly set z equal to 1. Of course, this diverges. So the trick is to multiply by e to the minus n, minus epsilon n log n. And then the sum becomes convergent for finite epsilon. And then you take the limit epsilon going to 0 plus. And this is a well-known, it's called Lindelof resummation method. And it turns out that it works. So this indeed gives you 1/3, which is indeed Q of 1. Questions? So, back to physics. Actually, this very simple procedure, it works for the Fermi polaron. So for the Fermi polaron, you can also write down a diagrammatic series using the ladder scheme. It looks very similar to the one I just wrote down for the equation of state of the gas, of the many-body gas. And it turns out that the series has a finite convergence radius. Actually, Chris Van Hoeke has some new numerical data which very clearly show that. And in practice, people have already applied the Lindelof resummation method, and it works very well. And it agrees with the ansatz of Frédéric, but he will not have time to present it today, unfortunately. That's really sad. Now that's the end of our excursion. And now let's go back to the resonant Fermi gas. So actually, back in 2012, you know, when we were young and naive, we just said, okay, let's assume that this is true, that our function is analytic at the origin. By the way, at the time, we had no idea how to construct the function, so we just postulate that it exists. And then we said, okay, let's try to apply Lindelof. And actually, it worked really nicely for the equation of state. Actually, that's the data that Frédéric showed to you. But now, and mostly thanks to our PhD student, who was very, very bright, we know that actually an diverges like n over 5 factorial. So it diverges faster than exponential, and therefore this cannot be true. So Q of z is not analytic at the origin. So therefore this Lindelof, even though it worked in practice nicely, apparently for the equation of state at least, mathematically it's not correct, in the sense that okay, we stopped at order 9 here, and we didn't go to very small epsilon, but actually if we would go to epsilon smaller than 1 over 5 before we do our extrapolations, then the thing would blow up. So in a way, we were lucky to get such good results, and well, we kind of understand it because this 1 over 5 is fairly small, but we cannot expect that this will work. And in fact, we had already seen that it didn't work very well when we tried to compute the critical temperature. So now that we know that we have this problem, the question, of course, is whether we are doomed. Because yeah, you can get very worried, because you can think that maybe now this thing cannot be unique anymore. Because, for example, if you have some function q of z, and you add some constant times exponential minus 1 over z, then what happens is that the Taylor series doesn't change. This is a well-known example of a function whose Taylor coefficients are all of them are 0. But of course, I mean, this is a different function. So and if you take z equal to 1, you will get a different result if you have this term or if you don't have it. So it looks like it's not unique anymore and we are screwed. Turns out that actually these kind of things don't happen in most physical problems, and in particular we think that it doesn't happen for the unitary Fermi gas. And yes? Okay, thanks for asking this again. I forgot to mention that now that we answered the point 1 that I already erased, but now that we constructed our function q of z such that the a_n's are the Taylor coefficients of this function, actually we can forget about the construction that we did in the beginning, starting from the bare scheme and reordering the diagrams. This we can completely forget about it, because we don't need it in our new story. So in the new story, we just say we construct this function, and these a_n's are the Taylor coefficients of this function. They are unique. They are very well defined. And it turns out that you can calculate them using these ladder diagrams, directly using the ladder diagrams. You don't need the bare scheme anymore at all. I didn't get your last point, but let's say it's true. So now, let me do a last excursion, and let's consider the anharmonic oscillator. So let's just consider Schrödinger equation, one particle in anharmonic potential. So the Hamiltonian is momentum squared plus position squared plus a coupling constant little z times position to the power 4. So the fact that the coupling constant here is called little z here is slightly unfortunate. It has nothing to do with the z coordinate. So that's why I use capital letters here for the coordinate of my particle. It's just a particle in one dimension, and the coupling constant, we call it z. So now the question is, what's the ground state energy of the particle in this potential as a function of z? And so the point is the following. So when z is real and negative, then your potential, of course, looks like that. Okay, when z is negative, this thing goes like down. And therefore, in fact, there is no ground state anymore. There is only a metastable state here, which will decay through tunneling through this barrier with a certain rate, gamma. And therefore, if you look now in the complex z-plane, this function E0 of z, actually, if you go on the real negative axis, it will acquire an imaginary part. And it turns out that this imaginary part changes sign if you approach from above or below, meaning that you have here a branch cut. And there is a discontinuity. So the function E0 of z, if you approach from above or below, it has a different value, and the difference behaves like exponential minus some constant over modulus of z when z goes to 0. So you see that you have a non-analyticity at the origin, but it's not at all something like that. Okay? Because this thing, if you approach from the left side, this will diverge very badly, while this guy actually goes to 0 very quickly when you approach the origin. So it's a singularity, if you want, which is much milder than this guy. And people have shown that indeed E0 of 1, So the value of the ground state energy here, where here, of course, your potential is just something like that, so it has a well-defined ground state energy. This can indeed be obtained using the Taylor series, so doing a perturbation theory in Z. And in practice, this is done by a resummation method, which is called the conformal Borel resummation method. I don't have time to explain it. Let me just mention that in order to design this method, you need to design some conformal mapping. And for that, it helps a lot to know what is the value of this A. And it turns out that this is nothing else than this gamma. So basically, you need to compute this tunneling rate. And this is how you can design the appropriate resummation method, which will achieve this goal. So indeed, yes, it's unique, and you can compute it for the anharmonic oscillator. Now back to the unitary Fermi gas, or resonant Fermi gas in general. So for the resonant Fermi gas, what we find is that the story is somewhat similar. So if you look now in the complex Z plane, our function Q of Z has some branch cut. Well, actually it has two branch cuts, which are at plus minus 4 pi over 5. And there is a discontinuity of Q of Z along this branch cut, which scales like, so again it goes to 0, e to the minus a over modulus of Z, but here it's to the power 5. And this is the reason why we get this n over 5 factorial here. And the fact that conformal Borel works for the anharmonic oscillator, but also for this more exotic situation, it's actually contained in a theorem which is called Nevanlina theorem, which is 99 years old, but most people actually didn't know it, including ourselves. So finally, I would like to present you in 5 minutes, if I can take five more minutes, I would like to talk a bit about the results that we got using all of this machinery. So, so far we only did calculations at unitarity and in the balanced case unpolarized. But polarized in principle is not a problem for us. So hopefully that will work well as well. And so we are in the normal phase, as I said in the beginning, and we went down to T over Tf about 0.19, which is already fairly close to the critical temperature. So Tc is experimentally was found to be at 0.16. I should say one thing. So for the lowest values of T over Tf, so 0.19 and a bit above that, actually the ladder scheme that I talked about is not applicable, and we had to use something more advanced, which we call the bold scheme, which is a self-consistent scheme. And basically the same arguments can also be applied to the bold scheme, even though in this case it involves some additional hand waving. So what we computed is the equation of state, of course, first of all. And the results agree with the ones we got in 2012. The error bars are smaller, and of course they are much more reliable, because actually back then we were using Lindelöf, which mathematically is not controlled. So now we hope that it's really controlled, and in practice our error bars are very small. So in particular we really resolve this story of the B4 coefficients that Frédéric mentions, because now we can have an accuracy of 10 minus 4 for our highest temperatures. We also computed the contact, and the momentum distribution. And so let me say a few words of physics about our results for the contact and for the momentum distribution. So first of all, about the momentum distribution. As you learned from Misha Baranov last week, if you would have a Fermi liquid, then at 0 temperature, or if you extrapolate to 0 temperature, you are supposed to get, a jump at the Fermi surface. So our data, they don't show this at all. So we get momentum distribution which is quite smooth. And you know, when we lower the temperature, okay, it becomes a bit sharper, but this slope does not at all seem to diverge if we extrapolate to 0 temperature. So we can say that we don't have a Fermi liquid behavior. Second point about the contact. So what we find is that the contact, if you make it dimensionless by dividing by kf to the power 4 as a function of t over tf, actually it varies very little. So if we go from t over tf equal 0.2 until say 0.8 or so, actually our results, they look pretty flat. It varies maybe by 10%, or if I remember correctly, which is quite surprising, because I mean you are doing really something dramatic. You go from a really degenerate regime, you are quite close to TC, you go to a regime which is basically non-degenerate. But actually the contact almost doesn't change. It almost doesn't change, and we actually understand why. In fact, this results from a competition between two effects. So in fact, there is really something going on here, but there are two effects which nearly cancel each other. And the two effects are the following. We can see actually the two effects if we plot the momentum distribution multiplied by K4 divided by KF4. So as you remember from my first lecture, this thing is supposed to approach C at large K. And indeed we see this very nicely in our data. We have a plateau here basically without statistical noise. So now let's see what happens for two different temperatures. So for example, here and here. So at a lower temperature, it will look something like that. So this is, say, T over Tf 0.2. Now if we go at a higher temperature, say 0.6, then it actually looks, well, like that. It's supposed to go out here and then back and then something like that. So, and now here is my story about the two effects. So what happens is that if you increase the temperature, the first effect is the following. So you go from something which is quite decreasing quite quickly at low temperature, you increase the temperature, then you will populate the higher momentum more. Okay? So this is why if you multiply by K4, this red guy, which is the higher temperature, it goes up much higher here. Okay? So this will tend to increase your contact because you see that, I mean, you go up very high, so then, okay, eventually you have to go down and to make a plateau, but if you are very high, then probably the plateau will be quite high as well. Okay. However, there is another effect which goes in the opposite direction. And the other effect is that you see that at low temperature, you start reaching this plateau much earlier. And the higher temperature you reach the plateau further away here. And the reason is very simple, is that actually in order to reach this n of k equal to c over k4 plateau, you need to have a momentum which is much larger than kf, but also much larger than the thermal momentum. And so here your thermal momentum, because you are at a higher temperature, your thermal momentum is somewhere here, and that's why you reach the plateau further away. So you have these two effects which compete with each other, and that's why in the end the contact almost looks boring. However, it's much less boring if you look at the MIT data, which are supposed to be published very soon. That was it. Thanks.